Welcome to this video on series and parallel circuits, where we'll be looking at series and parallel circuits. So let's go ahead and do that. Right, we've got two circuits out here. One of them is series and one of them is parallel. Pause the tape a second and be able to tell me which one is which and why. Which is series and which is parallel. Okay, so we should remember that the top one is series. And think back to our TV show analogy where we looked at, like we said, The Walking Dead. So in a series in a TV series, you have one show comes after another. And they usually come kind of chronologically. One episode comes right after the next. And that's kind of a reasonable analogy to look at a series circuit here, where we say that each component, as current flows through the circuit, it flows through one component after another. So the current goes, in our diagram, it goes from the positive end to the negative end. In actual fact, it goes from the negative end to the positive end because of that repelling force between the negatives of the electrons and the negative terminal, which we talked about in the last video. But here, series, components that come one after each other in line. So basically the clue you're looking for is components that kind of come in a line after each other. Then to come back to our TV analogy, then we had a parallel circuit, and we kind of talked about, we had the TV show The Walking Dead. Just make that black. We had the TV show The Walking Dead, and then all the events of that happened one after each other. So we had the storyline where things kept happening every episode. And then what was released was a TV show called Fear the Walking Dead, which was set in the same universe, didn't follow the same storyline, but it happened in parallel with the storyline, and the events of that show were in parallel with the events of this show, even though they never actually crossed. That's kind of a useful analogy to think about when we're talking about a parallel circuit, when we've got components that don't come one after each other. So as the electricity flow, the current comes out of the cell, part of it goes down here to this bulb, and then part of it also flows down here to this bulb. So this point here serves as a branch. So that current flows through the bulbs, and then it comes back here and it rejoins where it makes its way back to the cell. So this is the way that we've been representing parallel circuits like this. I'm just going to show you this kind of one other way that you might see them represented as well. It might come up in your exam, but it's perhaps unlikely. But the basic layout is the same. But then you might see parallel circuits kind of represented in this way, where here, in fact I'll make that different colour, at this point here, these are where the currents branch off and they flow through the bulbs and come back and then reach here and go on their way back. So it's the same principle as the one above, it's just represented slightly differently, but the way that we discern it is by identifying these branches. It branches off into branch 1 and branch 2, and then the current is split up across those, makes its way out of those, comes back to the cell, and so on. And remember that a circuit can be a combination of series and parallel. So you might have, in this example, you might have your parallel circuit, but then in there you might also find something like a resistor in there, which would be in series. So here it's in series as the current comes round, and at this point where it branches off it becomes parallel. Or you might then have an ammeter somewhere in the circuit here, which would be back in series. So Circuits are either series or parallel, or at times can be a combination of both. So here we'll take a quick look at how we use ammeters and voltmeters to measure current and potential difference. So remember that an ammeter, the circuit symbol is just a circle with an A in it, and a voltmeter, a circle with a V in it. An ammeter, to measure the current, which is I, and measured in amps, is always placed in series in a circuit. Always placed in series. You might sometimes see it at this location here, but always placed in series. And then a voltmeter, to measure potential difference across a component, because we're saying that potential difference is basically the number of volts across a component. The potential difference, we have to put the voltmeter in parallel. So we put it at the point here and the point here, and that tells us the potential difference that's going through that bulb. So a voltmeter always connected in parallel, and an ammeter always connected in series. So let's take a look at the way that current behaves in a series. So current in a series circuit is the same at every point. So it doesn't matter where you place the ammeter, whether it will be here, or here, or here, or here, or even here. If it read 1.5 amps here, then it would read 1.5 amps everywhere else. So it doesn't matter where you do it. So that's a rule that you need to know. Current in series is the same at every point. The current is always the same in series. So to come back to our river or water analogy that we've used in class, basically, if you had a nice river that flowed, you would find that the current at each point would be the same. There's nothing along the length of the river that's slowing it down or stopping it. So the current is always the same. So whether you measure the current here, the speed of the water here, or here, it would be the same. Let's now take a look at a parallel circuit and the way that current flows through that. So here we can say that total current, so that means the current that goes back here, goes back into the cell. If that was 6 amps going out, and we had 6 amps coming back, and we had 6 amps going out of the cell, it'd come down and it'd branch off, which would mean that this would then split up, and each of these would get 3 amps each of these bulbs, and then it'd come back, and then they'd join up again, and then they'd equal the 6 amps again. So total current is the sum of current in each branch. So the way that we kind of looked at in class was, we said that in a parallel circuit, current is shared through each branch. So come back to another water analogy. If we had a river flowing, and then in the middle of it there was some kind of, I don't know, big boulder or rock, then the water would flow through it. Let's say it flowed through at a speed of, I don't know, 10 miles per hour. And at this point it'd have to split up, and it'd slow down a little bit, and it'd be 5 miles per hour, 5 miles per hour here, but when it joins back up, it'd be 10 miles per hour again. Now let's take a look at the way that potential difference works in a circuit. So the thing to remember with potential difference, and it's important that you get these the right way around, potential difference behaves in almost the opposite way to current. So where in current we were saying that it was the same at each point around the circuit, that current was the same each way around the circuit, potential difference is not. So if we just add in another lamp here, we'll demonstrate that. I'm just going to add in another lamp there. Okay, and we're now saying that if we had 8 volts of potential difference, the current would come around, and here we might see that this one would get 3 volts, and perhaps this one might get 5 volts. So potential difference is shared across components in series. This is something you've got to remember, so watch this part of the video, quiz yourself on it, try and remember, try and write down the rules, check if you were right. If you were right, great. If you're wrong, go back, watch it again, try and remember it, write it out. Potential difference is shared across components in series. Current is the same at each point in series. Okay, so let's look at potential difference. Potential difference in parallel. Okay, so potential difference in parallel is almost like the way current works in series. If we have 9 volts of potential difference coming from the cell, then we get 9 volts in each of the bulbs. We saw that when we manipulated the circuits, and we found out that the bulbs tended to be brighter and of the same brightness when they were in parallel, compared with series circuits which got dimmer. So the rule in parallel circuits is that potential difference is the same in each component in parallel. And I need some handwriting intervention. And finally, let's find some space over here. Let's take a look at resistance in circuits, so in parallel and series circuit. So if we set up a circuit that looked like this, which had 2 resistors, like so, we could call this resistor 1 and this resistor 2. Well, the total resistance, RT, would equal the sum of R1 plus R2. So because we're in series here, in series, just to make that clear, this is a series circuit. In a series circuit, the resistance total is the sum of R1 plus R2. So if this resistor was 3 ohms and this one was 5 ohms, resistance total would equal 3 plus 5, so the total resistance would be 8 ohms. So the total resistance in the circuit would be 8 ohms. It's really, really simple maths. Really simple. It's just a sum. So let's take a look at resistance in a parallel circuit, and the rule is this, which might seem strange, but the total resistance is actually less than the resistance of each individual resistor. So the total resistance of the circuit is less than the resistance of each resistor in the circuit. So let's look at what that looks like actually in a circuit, and this will help to explain why in a parallel circuit as well some bulbs appear brighter and they get that equal distribution of potential difference. So in this example we'll just use the same resistors as before, which to remind ourselves was 3 and 5. So we've got 3 ohms here and 5 ohms here. Now I'm going to take a look at why the total resistance of the circuit, total resistance, is going to be actually less than both of these, less than even 3, which doesn't make sense really, because you think if you're adding resistors you should be increasing resistance, but when you add resistors in a parallel circuit you're decreasing the resistance in the circuit. Don't get too hung up on why this is the case, you don't particularly need to know that. You don't even need to know the formula for your exam on calculating resistance total in parallel. We don't need that. We only need to be able to calculate resistance total in a series circuit. So that RT equals R1 plus R2. You won't be asked about calculating total resistance in a parallel circuit. So don't worry too much about that. All you need to remember is that resistance in a parallel circuit, the total resistance is less than the resistance of each resistor. To be more specific, the total resistance of the circuit is actually less than even the smallest resistor. Remember, if you want to calculate resistance in a circuit, for example, if you want to calculate resistance in this circuit where we've got 9 volts flowing through each bulb, let's say we put an ammeter in here, and the ammeter is giving us a reading of 6 amps. I'm going to ask you to calculate the resistance of the lamp, of lamp number 1. So remember the formula that we need to use. We want to calculate, let's get our formula triangle VIR. We want to calculate resistance, so we're going to cover that up, which leaves us with R equals V over I. So resistance equals the potential difference, or the voltage, divided by the current. Now just have a moment and pause the tape, pause the recording, and tell me what numbers I'm going to put in at the top and at the bottom here. And let's see if you were right. Well, if you put 9 volts, you'd be correct. But if you put 6 amps, you'd be incorrect. You'd be incorrect because you haven't remembered the rule that in a parallel circuit, current is shared. So the total current is here is 6. We know that there are 2 bulbs, which tells us that each one of these bulbs must be getting 3 amps. So actually, the number that we need to use to find out the resistance of the individual bulb would be 3 amps. So R equals 9 divided by 3, beg your pardon. So R equals 3 ohms. So the resistance in this lamp is 3 ohms. Then we can assume then, because this is 3 amps and this is 3 amps and this is 9 volts and this is 9 volts, that both lamps have a resistance of 3 ohms. So remember to do that. If your ammeter is giving you the total current and you're being asked to calculate an individual component, remember that rule that current is shared. So you need to apply that to the component and divide that by however many components there are to calculate this. So questions that you must be able to answer, and if you can't answer them yet, go back through the video, quiz yourself, remind yourself, just keep going over and over it again. Try and write the answer down, see if you can remember. If you get it wrong, check it, write it down again. If you get it wrong, check it, write it down again. This is going to help you to remember. But the first question you need to do this with is, how does current flow through a series circuit? So what happens when it meets each component? How does current flow through a parallel circuit? How is potential difference distributed through a series circuit? How was potential difference distributed in a parallel circuit? What does resistance look like in a series circuit, and what is the formula for calculating total resistance? And the last question, what is the counterintuitive rule, so the rule that kind of goes against what we'd expect to see, about resistance in a parallel circuit? So what happens to the total resistance when we add resistors? Good luck, keep your eyes peeled for the practice questions and the walkthrough, which will be coming soon. Adios.